We're continuing our exploration of limits. So we said in class today that the limit, we said it yesterday too, the limit of a function has to do with what output value the function approaches without regard to what actually happens at that function value, at that input value. So here, I'm going to cross out what happens at x equals 2, and I can still figure out what I expected the function to do at the place where x equals 2. If I came from the left, I was headed to there. If I came from the right, I was headed to there. So I can say here that the limit of f of x as x approaches 2 is 2, because I can tell where I was going, even if something unexpected did happen. The limit is about what I was expecting to happen. The function value, I would say f of 2 equals 1. This understanding we have of a limit doesn't change what you know about how to read a graph. So here, if I asked about f of 2, I would say we're going to look at the graph at the place where x equals 2 and find out what y value got colored in. That's still 1. That's the function value, but the limit here is 2. So we looked at a graph today where we saw a function. We crossed out what happened at the x value, but we were headed to two different places. So that's what we have to look at today. We're going to talk about functions that are not well behaved. Let's clear that. Come here. So we said today that for a limit to exist, we have to approach the same function value from the left and from the right. So in order for us to be able to talk about what a function does from the left and what it does from the right so that we can compare them and make sure that they're the same, we've developed a notation for what we call one-sided limits. We're going to talk about limits as a function approaches a certain x value, certain input value from the left or from the right. So you'll see at the top of your notes paper, ooh, I left all the notation out. We're going to look here. I think you got a little peek at the notation today in class. Okay. So here I have a function f of x. If I examine this function at the place where x equals c, I don't know, I'm kind of in this habit now of crossing out what actually happens. The question is, can I still figure out what the limit as x approaches c is? Can I still tell where the function was headed? And I see I have this problem that we talked about, which is from the left-hand side, my function approaches the y value of k. And from the right-hand side, my function value approaches L. Those don't match, so I would have to say here that the limit is undefined. You can see I wrote up here another way to say that. The limit as x approaches c of f of x does not exist because the left and right-hand limits do not match. So let's talk about a notation for left-hand and right-hand limits. You can see here, you saw a little preview in class today. I would say this about the graph. I would say that the limit as x approaches c from the right of f of x is L. So that's how I read this notation. That's the limit as x approaches c from the right. The plus sign above the value I want my x to approach, I read that as from the right, from the place where numbers are closer to being positive or are more positive. This other limit, I would say the limit as x approaches c from the left of f of x. Where was I headed? What y value was I headed to if I come along the function from the left? I was headed to there, which is labeled k. So the limit as x approaches c from the left of f of x is k. Did you notice there's a place on your notes to write that in? I wrote in the words I said. It's your job to write in this, notation. This is you learning the notation for right-hand limit and left-hand limit. And then theorem 3. This is the first calculus fact I need you to memorize by heart. You'll see that the first math practice for AP Calculus that I'm expecting you to utilize in your work is the ability to reason using theorems. So this is our first theorem. It's not that theorem 3 is any special name, but this is the theorem that tells us when a limit exists. So there's a place on your paper to write it out in words and a place to write it out in symbols. So you can see here, I just copied and pasted this from your textbook, so you can look in your textbook too. A function f has a limit as x approaches c if and only if the left-hand limit and the right-hand limit are equal. So what's written down below in symbols is one good way to write that. The limit as x approaches c is going to equal L. The limit of f of x as x approaches c is L if and only if both the right-hand limit is equal to L and the left-hand limit is equal to L. That's the best way to write it out. So that you see there's a place for that in your notes. Write it in. All right, this next example, I gave you this graph and I asked you to tell me about the left-hand limit, the right-hand limit, and the limit at a bunch of different x values. And also tell me the function value. So I actually have like all this written out, and there's 5 different values, x values I want you to explore. You might have to squeeze really hard to get all that information on your paper. Feel free to use a separate piece of paper. I had to do it nice and big so that you can still read it and not see it too squished. So I asked you to start with, the first x value I put there was x equals 0. So I'm going to actually start with x equals 1, and we're going to talk about the endpoints because they're a little bit special. So at x equals 1, I've written here that the left-hand limit, the limit as x approaches 1 from the left of f of x is 0. Here's the point I'm looking at. As x approaches 1 from the left is the y value 0. The limit as x approaches 1 from the right is here. You can see I came in from the right-hand direction. The actual function value refers to the place at x equals 1 where the dot got colored in. That happens to be the y value 1. So then the question is, does the limit as x approaches 1 of f of x exist? My answer here is no, the limit does not exist because the left-hand limit and the right-hand limit do not match. If I asked you to justify that on a test, or if you had to justify that on the AP test, let me show you how I would write that. I would say the limit as x approaches 1 of f of x does not exist because the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. All right, continuing. So the next x value, we might explore at x equals 2. The limit as x approaches 2 from the left is the place I was headed to, which is y equals 1. The limit as x approaches 2 from the right, the place I was headed, happens to also be 1. The function value is the y value they got colored in. That's all the way up there. That's 2. But I can say that the limit does exist because the left-hand limit and the right-hand limit match. The limit is not about what actually happened, but from the left I was approaching y equals 1, from the right I was approaching y equals 1. The limit as x approaches 2 is 1. At x equals 3, the limit as I approach from the left, the limit as x approaches 3 from the left is 2. The limit as x approaches 3 from the right is also 2. So the limit as x approaches 3 of f of x is 2 because the left-hand limit and the right-hand limit match. Now coincidentally, f of 3 is also 2. So here the actual behavior matches what I was expecting, and so the limit does exist. Notice that this was not a requirement for the limit to exist, it just happens to coincidentally happen. We'll see if that's important in the next chapter. Okay, so we have 2 more places to talk about. That's x equals 0 and x equals 4. So let's take a look here. At x equals 0, if I try to find the left-hand limit, if I want to walk along the function from, oops, here's my pen, from the left, notice there's nothing to walk on. So I can't do it. I can't figure out what the left-hand limit would be. The right-hand limit, that's pretty easy. I'm going to walk around the function from the right toward the place where x equals 0, and I get the limit 1. The actual function value is colored in. That's 1. But I can say here that the limit does exist because the right-hand limit is 1, and there's no domain to the left of x equals 0 for me to walk along. If there were x values over there, I would have to walk along them and see where I was headed. But there wasn't even anything to walk on. So since the domain to the left of x equals 0 is not part of this problem, I don't have to worry about a left-hand limit. I can just focus on the right-hand limit. So the right-hand limit exists and is 1. So you can probably guess at the place where x equals 4, it's the left-hand limit that I can figure out. I can walk along this function from the left toward the right, and I see I was headed toward y equals 1. There are no values over here to the right of x equals 4 for me to walk along, so I don't have to worry about the fact that I can't tell what the right-hand limit is. I can tell what the function value is, and that's f of 4 is 1, because that's colored in. And I can say the limit does exist. The limit as x approaches 4 of f of x is 1, because the left-hand limit is 1. As I approached from the left, I got a y value of 1. And there aren't even any domain values to the right for me to worry about. So here, the limit does exist. We call this is still called a one-sided limit, but it's a limit at an end point. So I would say the domain of this function appears to be 0 to 4 inclusive. So to the left of 0 or the right of 4, I don't have to worry about being able to say what the limit is.